Look closely at the solid objects around you. Beneath their stable surfaces, two opposing chemical extremes are constantly seeking a chance to react. Chemists classify these as acids and bases. Acids act as proton donors, while bases act as proton acceptors. Both exist in a state of chemical tension, constantly seeking to interact and reach equilibrium. Because this chemical tension is not visible to the naked eye, scientists rely on specialized materials called indicators to act as early warning systems. When exposed to these extremes, a strip of litmus paper will shift from blue to red in the presence of an acid, or from red to blue for a base. Even smells can act as alarms. The distinct scent of vanilla extract will vanish entirely if it encounters a strong base. These sudden shifts in color and smell are direct warnings of a highly reactive environment. To understand why these environments are so volatile, we have to look at what exactly these chemicals do to the solid matter they touch. Inside the laboratory, we can observe how these chemical extremes dismantle otherwise stable materials. This diagram illustrates a classic reaction. When an acid reacts with zinc metal, it breaks the solid down, releasing hydrogen gas that ignites with a pop near an open flame. Here is another illustration showing a different type of breakdown. When acids encounter solid metal carbonates, they tear the compound apart, generating a steady stream of carbon dioxide gas that travels into the neighboring solution. Acids can even strip apart solid metal oxides, like copper oxide, dissolving a dark powder until it becomes a clear bluish-green liquid. Whether it's breaking down zinc or dissolving copper, we have to ask, how exactly are these liquids tearing solid structures apart? The destruction you see at the surface is the result of microscopic instability. These liquids are packed with components that must either steal or discard parts of themselves to reach a balanced, neutral state. Zooming down to the atomic level, we find that the actual agents of this destruction are electrically charged particles known as ions. The schematic shows how we prove they are there. When graphite rods are submerged in an acidic solution, the bulb lights up, confirming the liquid is swarming with free-flowing charged ions capable of carrying an electrical current. The type of ion defines the chemical. Acids release positively charged hydrogen ions, while bases release negatively charged hydroxide ions. But neither acts alone. A completely dry acid remains inactive. It requires water to physically surround the molecules and pull them apart into free-floating ions. When chemists label an acid or base as strong or weak, they are making a specific calculation. They are measuring the concentration, the sheer physical number of these loose ions floating in the water. All the bubbling gas, dissolving solid metal, and the shifting colors we witnessed are simply the visible result of millions of these invisible hydrogen and hydroxide ions searching for something to bond with. So what happens when you pit the ultimate proton donor directly against the ultimate proton acceptor? The moment a strong acid and a strong base collide, the free-floating hydrogen and hydroxide ions instantly snap together. Their opposing electrical charges perfectly cancel each other out. Through this molecular clash, called a neutralization reaction, the two corrosive extremes resolve entirely into harmless salt water. This is the pH scale, our tool for measuring these reactions. It tracks the exact concentration of hydrogen ions across a spectrum, moving from the highly acidic red zone near 0 through neutral green at 7, down to the basic dark zone at 14. This scale provides a direct, mathematical measurement of chemical power, allowing scientists to safely predict how any solution will behave. Working with these concentrated materials in a real-world laboratory requires strict adherence to physical safety limits. Mixing a concentrated acid or base into water causes the molecules to dissociate and release their ions all at once. This triggers a massive release of energy, an exothermic reaction that generates extreme heat. Because of this intense heat, there is an unbreakable safety protocol for dilution. Always add the concentrated acid slowly into the water. If you pour water directly into a strong acid, the rapid heat generation can cause the mixture to boil and splash. By identifying the specific behaviors of hydrogen and hydroxide, the mechanism of chemical corrosion becomes predictable. When we apply these principles, we turn reactive chemistry into a precise tool for shaping the physical world.